Hello everyone, I'm F1YYY, a senior security researcher at Chiton Technology. I'm gonna present a disaster caused by a bug, a black box escape of Qemu based on the USB device. I will analyze a vulnerability in Qemu, which has an important impact on the public cloud. I will also share a new exploit method. Our new exploit method can be used to escape the public cloud without any additional information, which we call a black box escape. Now, let's start. I come from the Chiton Security Research Lab. Our security research lab has researched lots of practical targets in recent years, including PS4 jailbreak, Android routing, IoT offensive research, and so on. Furthermore, we play CTF with Team Bloop and T-Delivers. We are also the organizer of real-world CTF. We create many hard and real challenges every year. If you are interested in it, we welcome you to participate in our CTF game. And my partner, Lingni and Haipeng, come from the Information Security Lab of Ocean University of China. They also play CTF, and now they are focusing on automated exploits. If you are a software engineer or a security researcher, you probably have used virtualization software such as VirtualBox, Qemu, VMware Workstation, and so on. But you probably have not heard about virtual machine escape. What is a virtual machine escape? In normal circumstances, guest OS runs on the hypervisor. When the guest OS executes some sensitive instructions or communicates with the hardware, hypervisor will handle it. The host emulates virtual hardware and handles RPC requests for the guest. Guest OS is isolated from each other and cannot affect host OS. However, if there are some vulnerabilities existing in the host emulation part, it's possible for the guest OS to escape the virtual machine environment. Guest OS can communicate with the virtual hardware and exploit the vulnerabilities. In this way, it can execute arbitrary codes on the host, and this is the virtual machine escape. Now, before we start the vulnerability and exploit, let's see how the Qemu-KVM, the most popular public virtual machine, works. Qemu is an open source emulator. It's developed for emulating many old or new devices. And the KVM is the short of kernel-based virtual machine. It's a kernel module which encapsulates Intel VMX or AMD SVM for the user space. So, they are combined to get better experience. Qemu will emulate many devices for the guest virtual machine, including net card, disk, graphics card, and so on. KVM will emulate the CPU and memory for the guest virtual machine by using VMX or SVM. Qemu will use IO control and double KVM, which is an API provided by the KVM to control KVM build and run guest virtual machines. and the libvirt, which is widely used when you run a Qemu-KVM virtual machine, is a set of open source APIs, daemons, and management tools for managing hardware virtualization. In short, it offers many documented API for users and software engineers to manage and run virtual machines. Most public cloud providers use libvirt. So, what's the attack surface of a libvirt virtual machine? We all know that the most important attack surface of a virtual machine is the virtual device. libvirt creates virtual machine with some virtual devices, UHCI with HID connected, and graphic card series VGA. It's all the virtual devices you have when you start a virtual machine managed by the libvirt. Virt.io is an I/O paravirtualization solution. It's designed for faster and lighter. So the logic of the Virt.io device is simple, and it also has field code and CVEs. Series VGA is an old graphics card. There are some vulnerabilities found in Series VGA, but most of them exist in the process of graphics-related memory operations on an independent continuous heap memory. It means that even if you've got a heap overflow vulnerability, you are only able to crash the virtual machine. And the last target, UHCI with HID connected. UHCI is short for Universal Host Controller Interface. It's also known as USB 1.0. HID is short for Human Interface Device. For example, it includes the mouse and the keyboard we use every day. So, why is it hard to escape from the public cloud? Imagine that you are a security researcher and work for a public cloud provider. Your company is still using an old version of Qemu-KVM. You think it's dangerous. But your boss needs you to prove that an attacker can easily attack your cloud. How do you prove that? It's hard to prove that before, because first, we lack good vulnerabilities. All the vulnerabilities you found cannot be used to escape the libvirt virtual machine. Second, it's hard for an attacker to obtain some key information. Almost every escape exploit needs additional information, like the binary of Qemu. It's hard for an attacker to get this. So, that's why we think that black box escape is important when we analyze the security of the public cloud. Now, let's start analyzing CVE-2015-5165, the most important vulnerability in Qemu. It's a vulnerability existing in the Qemu USB device. This vulnerability was reported to Redhat on August 13, 2012, and Redhat fixed and disclosed the vulnerability on August 24, 2012. Before analyzing the cause of it, we need to learn how USB packet transfers from the guest OS to Qemu first. Let's take UHCI as an example. The driver in guest OS will send USB packets by writing 4 registers of UHCI, including FL base address low, FL base address high, FR number, and command. When writing the command register, it's possible to make the UHCI start to prepare a structure, which stands for the USB packets we want to send. Then, the USB packets will be transferred from the UHCI to the control endpoint or data endpoint of the USB device. The vulnerability we are talking about exists in the processing of the UHCI transfer USB packets. So, how do Qemu transfer packets from UHCI to the USB device? First, there are 3 types of USB packets in the USB transmission protocol, including setup, data in, and data out. Qemu will check the type of the USB packets. If the type of the packet is setup, then it will check if it's a dear out or dear in packet. A dear out setup USB packet means that the driver or you want to set some control information of this USB device. A dear in setup USB packet means that the driver or you want to get some control information from the USB device. If it's a dear out setup USB packet, then the Qemu will wait for the data of this setup packet. And you need to send another data out packet. Once the data has been padded, all of this will be sent to the control endpoint of the USB device. If it's a dear in setup packet, then the Qemu will just transfer it to the control endpoint of the USB device. There will be some back data from the USB device. You need to send another data in packet to read the data back. If it's a data in packet or a data out packet, Qemu will just transfer it to the data endpoint of the USB device. This is the general logic of Qemu processing packet transmission. The vulnerability we are talking about is in the processing of the setup packet. Here is some code in the function do_token setup. This function is used in Qemu to handle setup packets. As the code shows, it copies the data in the USB packet to the setup buffer first. The data of the USB packet comes from the guest, which means that we can control it. Then it clears the setup index and the actual lines. Next, it gets a setup lines by combining the 6th byte and the 7th byte in the setup buffer. The setup lines stands for the data lines of the control information we want to get or set. Then, it compares setup lines with the size of the data buffer. If it's bigger, then the check fails. But before returning, this function does not clear the setup lines. So here comes a problem. Let's see what happens when we send another data out USB packet. Qemu uses a function named do_token_out to handle it. As the code shows, if the setup state is setup state data, it will copy data between the USB packet we send and the data buffer by using the setup lines. So, how do we build a POC? We can build a POC in 3 steps. First, we send an 8-byte setup packet. The 6-byte is 0x80 and the 7th byte is 0. We will set setup state to be setup state data after sending it. Second, we send another 8-byte setup packet. The 6th byte and the 7th byte is 0xFF. This packet will set setup lines big enough, and it will fill in the check. Thirdly, we send an n-byte data out packet. Then there will be an overflow write to the data buffer. So that's the vulnerability and how we build a POC for it. Now, let me share our black box escape method. First, why do we need black box escape? Just like the example I took before, it's hard for an attacker to get some key information, like Qemu's version on the binary field of Qemu. So it's important for us to find a method which does not need this. So what do we have now after building the POC? It's obvious that we can do out-of-bound read and write of the data buffer between 0 to 0xFFFF. So how do we link some key information? After analyzing the USB device structure, we find that the USB describe structure pointer contains the description of this USB device. We all know that every USB device has its own vendor ID and product ID for the driver to identify what this USB device is. Qemu emulates this by using the USB description structure. We can get all the USB description ID in the guest by sending some normal USB packets. So here comes the idea of arbitrary address reading. We can overwrite the pointer of the USB description and then get the USB description ID back to do an arbitrary address read. Now, we can do arbitrary address read if we want to run some commands in the host OS to prove that we escape from the guest virtual machine. Using the system function in the libc is a way to do it. So next, we try to get the address of the system function. We find that the USB endpoint structure has a pointer to the USB device, and there is a free function pointer in the USB device state structure. But this free pointer does not point to the free function in the libc. It points to the PLT segment in a shared library. We pass the code in the PLT segment and read back the address stored in the GOT segment. Finally, we get the free function address in libc. After getting the address of the function free, we get the address of the function system like dynelf does in pointtoys. We search for the ELF magic number forward first to get the base address of the libc. Then we find the dyn string and the dyn symbol sections by passing the header of the ELF. And finally, we search for the system string in the dyn string section and get the offset of the system function in the dyn symbol section. Now, we get the address of the function system. Then, we consider how we control the workflow. We find that there is a function pointer in the HID state structure. We are able to call it by sending some USB packets to the control endpoint of the HID device. So, we overwrite the event function pointer to the address of the system and overwrite the head of the HID state structure to the command we want to execute. And finally, we successfully escaped from the guest. Here is a demo we recorded. We use Vault Manager to run the guest virtual machine. And finally, we pop a calculator. Here comes a conclusion. First, I think that sandboxes are necessary even in public cloud environments. Sandbox is a good toy to protect the vulnerable part, and it has been widely used in browsers. However, there may be a lot of work to be done on the design of the sandbox. Second, good vulnerabilities can do a lot of interesting things. Escaping from the guest is only one of them. Like the vulnerabilities we show, we are also able to dump the memory of the Qemu process. We can get all the fields including Qemu, many shared libraries, and so on. It's even possible to run some shellcodes. If there is a sandbox, we can test the sandbox in our shellcode and try to bypass it. So, good vulnerabilities bring us more possibilities. And third, the skills used in CTF are really helpful. Someone has told me that the skills you learn in CTF are useless in real vulnerability, but in our exploit method, we use many skills in CTF. And that's all we want to share. We also wrote a white paper which contains all the technical details. If you've got any questions about all of this, you can contact me through Twitter. Here's my Twitter. That's all. Thanks for your watching.